Mars, our planetary neighbor, it's very cold and dry, and its weak gravity only holds a thin atmosphere. As probes started to visit the red planet, we gained a more accurate view of the surface, and scientists began to wonder. Mars had once been much warmer. It had rivers and, in its early years, might have sustained life. A succession of new techniques has been deployed, trying to unlock the secrets of the red planet. And while our knowledge of Martian geology, its atmosphere, and its weather has grown immensely, each new mission to Mars raises more questions than it answers. We still don't know if Mars has at some time been a home to life. In 1877, astronomer Giovanni Schiaparelli made what he thought was the most accurate map of Mars yet drawn. On it he showed canals. In the early 20th century, American astronomer Percival Lowell was convinced the canals were signs of a civilization existing on the red planet. So began the search for life on Mars. In 1962, the Soviet Union sent the first probe, the Mars M1, on a flyby mission. It was an audacious project, and it failed, the first of many failures by both the Soviet Union and the United States. Cold War rivalry provided the motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars. It was the first probe to orbit another planet, but scientists discovered that Mars was enveloped in a planetary dust storm. On-orbit photography revealed little more than a red cloud. Soon, Mariner 9 was joined by two Soviet orbiters, both equipped with landers. The Mars 2 lander crashed, but the Mars 3 lander made it to the surface intact. It returned one garbled image and then stopped functioning. Mars now had 3 orbiting spacecraft, all looking at a dusty, featureless planet. The two Soviet probes were identical, but the American probe had one key design difference. While the Soviet orbiters began photographing the planet following predetermined schedules, NASA was able to command Mariner 9 to wait, in hope that the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was called the Tharsis Plateau. Soon, more complex geological features began to emerge. In places, the surface was cratered, suggesting the tectonic forces that constantly renew the Earth's surface were absent on Mars. Volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. Viking 1 and 2 were identical orbiters with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life, but researchers now feel the 3 experiments tasked with carrying out the analysis had limitations. As researchers on Earth began looking for traces of life in extreme environments, they began to rethink where life on Mars might survive. Yet the consensus at the time was that Mars was sterile, and the idea of life on Mars died. After a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the red planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas. But the occasional impact crater suggested that nothing has flowed in these systems for billions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times, cut budgets, and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface. To do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site in Mars' northern hemisphere, known as Ares Vallis, is one of the planet's rockiest areas, yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. Pathfinder consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that, at its closest approach, had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months and saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle. Though all contact was lost with the lander, Mars Express continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Equipped with a high-resolution stereo camera, the probe returned unique 3D views of the planet's surface. The orbiter determined that the polar ice caps contain a blend of frozen CO2 and water ice. In the atmosphere, Mars Express detected first methane and then ammonia. Both gases deteriorate rapidly in sunlight, so there must be sources on Mars continually producing them. Methane and ammonia can rarely be made inorganically, but they're generally associated with life. 1 month after Mars Express went into orbit, a NASA lander arrived at Mars, followed 3 weeks later by a second, identical craft. They were the Mars exploration rovers called Spirit and Opportunity. Spirit, the first to land, was targeted at the Gusev crater. Opportunity would land at Meridiani Planum on the opposite side of the planet. Though they were much heavier than their Pathfinder predecessor, they used the same bounce landing technique. Both landings were successful and on target. After the craft had righted itself, it detached from the lander and began autonomously unfolding its solar panels and camera mast. While this was happening, the team back at the Jet Propulsion Laboratory waited. Signals confirming the craft's safe arrival took 15 minutes to travel back to Earth. Many of these people had invested years of their lives in this project, and the real mission had only just commenced. Both rovers were designed to operate for 90 Mars days. A solar day on Mars is about 40 minutes longer than an Earth day, and to avoid confusion, the science team operating the rovers refer to a Martian day as a sol. Mission designers, knowing about the dust storms on Mars, felt that the solar panels on the 2 rovers would eventually be blocked with dirt and stop functioning. But it became clear that the winds on Mars were clearing the panels. Soon, NASA announced that Opportunity had found evidence confirming liquid water had once flowed on Mars. There were pictures from the Meridiani Planum of stratified patterns in the rocks, suggesting sedimentation. The distribution of chlorine and bromine at the site were clues to the areas passed as the shore of a salty sea. In April, NASA announced it would extend the rover's missions from 3 to 8 months. It would be the first of many such mission extensions. The rovers were equipped with an abrasion tool to grind away a portion of a rock surface for a more detailed, uncontaminated analysis of geological samples. This was first done by Spirit at a rock named Adirondack at Gusev crater. It was a first in planetary geology. Researchers agonized before using the tool because of the drain it makes on the rover's energy budget. The rock was made of olivine, pyroxene, and magnetite, making it very similar to volcanic basalt on Earth. When Spirit's right front wheel stopped working, engineers used a duplicate rover to devise a reversing technique that enabled the rover to drag its frozen wheel. This left a furrow behind in the soil, which presented a new area of research for the science team. White or yellow deposits seen within the furrow were various types of salts that only form in the presence of hot water. On Earth, hot water provides an environment in which microbes can thrive. Spirit limped on for another 3 years before it became stuck in loose sand. Again, the engineers began working with a replica which they placed in an identical situation. When nothing was able to free the rover, it was declared a stationary research platform. Further attempts were made to position the rover so its solar panels could operate more effectively, but even this was not possible. The last communication from Spirit was in March 2010. Opportunity lasted until June 2018, when dust clogged its solar panels. In March 2006, NASA's Mars Reconnaissance Orbiter arrived at Mars and began the now routine business of aerobraking. Though this procedure took roughly 6 months, the saving in fuel will see the craft functioning at Mars by the 2030s. One of the most important roles of the newly launched Mars Orbiter was to serve as a powerful communications relay station. It came equipped with a massive 3-meter wide antenna capable of transmitting in the ultra-high frequency band, which dramatically increased the rate at which data could be sent back to Earth. In fact, by November of 2013, this new orbiter had already tripled the amount of data transmitted to Earth when compared to all other NASA Mars missions combined. Alongside its communication capabilities, it carried a high-resolution camera that began capturing images of the Martian surface with incredible detail, revealing things never seen before. These high-definition images offered glimpses into the active geological processes still taking place on Mars. One area in particular, East Coast Chasma, showed dunes in the act of falling, proof that wind and movement were reshaping the surface even now. In the polar regions, which are typically coated in seasonal dry ice, the orbiter revealed patches that had become free of ice, exposing the terrain beneath. In the southern hemisphere, strange pits were found in the residual carbon dioxide cap, features that sparked interest due to their unusual shape and unknown origin. These findings heightened interest in the Martian poles, which scientists believed held clues about the planet's past climate and water history. This surge of interest led to NASA's Follow the Water campaign, a mission strategy centered on tracing water in all its forms on Mars. The Phoenix lander was chosen to target the planet's northern polar region based on data from the Mars Odyssey mission, which had suggested that frozen water might lie just below the surface. Since satellite imaging showed the area to be flat and featureless, NASA decided that a rover would be unnecessary. Instead, a stationary lander would be deployed, designed to decelerate using a parachute combined with rocket thrusters to safely touch down on the surface. However, this descent strategy stirred up some controversy. Unlike previous rovers that used bouncing airbags to land, Phoenix used controlled rockets. Some scientists expressed concern that the exhaust from the landing rockets might contaminate the very ground the mission was meant to analyze. To mitigate this, Phoenix waited a full 15 minutes after landing before deploying its solar panels, allowing the dust kicked up by the rockets to settle. The timing was intentional. Phoenix landed during the early Martian spring in the northern hemisphere, ensuring its solar panels would receive maximum sunlight to power its instruments for the planned 90-day mission. In addition to its camera mast, Phoenix was equipped with a fully functional meteorological station, allowing it to measure Martian weather every day. The station included wind indicators as well as sensors for pressure and temperature. One of its most surprising features was a LiDAR system, an instrument that pointed vertically and could detect fine atmospheric details. Using LiDAR, Phoenix observed cirrus clouds forming high above and even recorded the delicate spectacle of snow falling through the Martian sky. These observations were groundbreaking. Never before had snow been seen falling on Mars, adding a new layer to our understanding of its climate systems. Phoenix also came with a robotic arm capable of digging up to half a meter into the soil. The purpose of this arm was to scoop soil and ice samples and deliver them to a built-in analyzer. This device used a series of 8 high-temperature ovens, combined with a mass spectrometer, to detect chemical elements and compounds. In one particularly revealing dig, Phoenix's camera captured a patch of white material that gradually vanished over time. Scientists quickly concluded that it could only have been water ice, which had sublimated, turned directly from solid to gas, after being exposed to the open Martian air. The soil samples told a mixed story. While they were found to be slightly alkaline, a potentially favorable sign, another discovery tempered any optimism. The presence of perchlorate, a chemical known to kill bacteria on Earth, suggested that the Martian surface might be more hostile to life than hoped. Despite these challenges, Phoenix operated far longer than its original 3-month plan, surviving for an additional 2 months until the advancing winter plunged the region into darkness. As the sun dipped below the horizon, the lander's solar panels were left without light, bringing the mission to an end. While the surface held little remaining water, the subsurface ice was now a confirmed reality. Researchers came to a crucial conclusion. Many of Mars' iconic surface features, such as dry valleys, carved channels and deltas, could only have been shaped by running water. Samples from different locations on the planet backed this theory. Water had once flowed across Mars in abundance. This realization raised the ultimate question. If Mars was once more like Earth, where did all that water go? And more importantly, had life ever emerged during that warmer, wetter time? Or could it still be hidden underground beyond our current reach? With these questions in mind, NASA prepared for its most ambitious Mars mission to date. The mission, named Curiosity, featured a rover the size of a car, packed with advanced instruments and powered by a nuclear battery. Unlike previous rovers that relied on solar power, Curiosity wouldn't be hindered by dust accumulation or seasonal darkness. Its power source allowed it to operate day and night, no matter the weather. In November 2011, Curiosity was launched aboard an Atlas V rocket from Cape Canaveral. It was destined for Gale Crater, a region believed to hold vital clues to Mars' ancient environment. The landing was watched with high tension at NASA's Jet Propulsion Laboratory. The Martian atmosphere is incredibly thin, and it doesn't allow for smooth, controlled landings like Earth's. The parachute used in Curiosity's descent could only slow the craft to about 320 kilometers per hour. That was still far too fast. As it neared the surface in mid-2012, the descent stage separated from the aeroshell, firing rocket thrusters to slow the fall even further. Radar guided the craft precisely, and a camera recorded the approaching terrain. But then came the most dramatic moment: the use of a sky crane to lower the rover onto the ground. This daring technique involved suspending Curiosity on cables beneath the descent stage, allowing it to be gently lowered onto the surface without kicking up dangerous clouds of dust. The sky crane then detached and flew off to crash at a safe distance. Miraculously, everything worked perfectly. The landing was not only a success, it was the most precise Mars landing in NASA's history. The engineers and scientists erupted in celebration. Once on the surface, Curiosity took an entire day to run internal checks, ensuring all systems were functioning properly before it deployed its mast cameras and communication antennas. Gale Crater, the landing site, was chosen for a reason. Scientists believed it had once contained a lake, with sediments that had settled first by water, then later by wind. It was estimated to be between 3 and 3.5 billion years old, offering a chance to explore Mars' ancient history layer by layer. With Curiosity now acting as a mobile science lab, and its data linked back to Earth through the Mars Reconnaissance Orbiter, NASA had its most powerful research platform yet on the Red Planet. The main goal was to determine whether conditions suitable for life had ever existed, or still might, in this region of Mars. But Curiosity's mission extended beyond the search for past life. It also collected vital data about present-day Martian conditions, including radiation levels, which are a key concern for any future human missions. The rover drilled into rocks and analyzed their dust, detecting critical elements like sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all considered essential building blocks of life. In its first 6 years on the Martian surface, Curiosity traveled about 20 kilometers. That may not sound far, but considering the rugged terrain, it's a significant achievement. Along the way, the rover continuously sent back self-portraits, mainly for diagnostics and system checks. However, the journey was beginning to take a toll. Curiosity's wheels had suffered significant wear and tear from the sharp rocks and rough Martian landscape. The damage was so severe that engineers started planning for changes in the design of future rovers. In addition to the physical strain, the rover's computer systems were also showing signs of aging. Still, Curiosity kept going, and its mission laid the groundwork for a new wave of Mars exploration. By 2020, a fresh lineup of missions was being prepared to continue this effort and deepen our understanding of the planet's complex past and present. One area of Mars, though, had remained largely unexplored: its interior. To address this, NASA launched the InSight lander, a mission designed specifically to study Mars' geological activity. InSight touched down flawlessly on the flat plains of Elysium Planitia, near the Martian equator, in November 2018. After deploying its solar panels, the lander spent several weeks surveying the surface to find a suitable location to place its seismometer. The goal was to detect Marsquakes, offering insights into the planet's internal structure and helping explain how and why Mars evolved so differently from Earth. In addition to its seismometer, InSight came equipped with a heat flow probe, sometimes called the MOLE, designed to burrow into the Martian soil and record temperature changes beneath the surface. Though the MOLE faced some challenges in drilling deeper, the data it did gather offered important clues. By studying how heat moves through Mars' crust, scientists could better understand how the planet's core functions, and how it once may have supported a more active, dynamic environment. These investigations helped scientists piece together how Mars lost its magnetic field, thinned its atmosphere, and became the cold, dry world we see today. Shifting focus beyond Mars, the next great mystery lies with the planet Saturn. Towering over Earth in size and surrounded by majestic rings, Saturn has a metallic core buried beneath more than 880,000 kilometers of swirling liquid hydrogen and helium. It's known as a gas giant, a world without a solid surface. Saturn is accompanied by over 62 known moons, each unique, with some hiding oceans beneath icy shells, while others exhibit mysterious geysers or thick atmospheres. Our best look at Saturn came through the Cassini probe, which orbited the planet for years before being intentionally plunged into its atmosphere in 2017 to prevent contaminating its moons. Even when viewed from telescopes on Earth, Saturn's rings are visible, but they appear as a thin, flat line. For centuries they were thought to be solid disks. It wasn't until detailed mathematical studies were done that scientists realized the rings were actually made of countless orbiting particles, ranging in size from dust grains to large boulders. But their origin remains a puzzle. Why does Saturn have such elaborate rings while the other gas giants have far more modest ones? These questions pushed scientists to dream bigger and explore farther, and Saturn became a central target for future space missions. Back in the 1960s, when the space race was still young, Saturn seemed almost unreachable. Rockets of the time could barely reach Mars. But in 1964, a team of NASA engineers had an ambitious idea. If a spacecraft were launched in 1977, it could take advantage of a rare planetary alignment. This unique window allowed a probe to fly past all the outer planets, Jupiter, Saturn, Uranus, and Neptune, by using gravity assists. The plan was bold, risky, and ahead of its time. It was dubbed the Grand Tour, and 2 probes would be built to take on this incredible journey. In 1995, the world was still marveling at what Voyager 1 and 2 had accomplished. These spacecraft weren't just historic, they were technological masterpieces, built with impressive durability to survive deep space missions far beyond what had been attempted before. Unlike their predecessors, the Pioneer probes, Voyager 1 and 2, were equipped with more advanced instruments, built to collect detailed data over long durations. This robust design would prove essential as they embarked on their grand tours of the outer planets, where conditions were harsh and the distances nearly unimaginable. Voyager 1, for instance, would soon begin one of its most exciting chapters. In late 1980, Voyager 1 arrived at Saturn, one of its key mission targets. Though its high-resolution polarimeter had failed, the spacecraft still returned invaluable images and discoveries. One of the standout moments was the first-ever detection of the G-ring, a thin, faint ring orbiting about 100,000 kilometers above Saturn's cloud tops. This was an astonishing find, and for the first time, researchers observed how Saturn's rings moved and behaved. They spotted strange, uneven patterns in the rings, features that came to be known as spokes. These spokes, scientists believed, were likely caused by electrostatic charges lifting tiny particles from the rings into Saturn's magnetosphere. As the data poured in, the pace overwhelmed scientists at NASA's Jet Propulsion Laboratory, JPL. After years of waiting and careful preparation, Voyager 1 was now delivering discoveries faster than researchers could process them. One of the most highly anticipated targets was Titan, Saturn's largest moon and the second largest in the solar system. Voyager 1's trajectory had been chosen specifically to pass close to Titan, which had long intrigued scientists because it was the only moon known to possess a thick atmosphere. However, the excitement turned to slight disappointment when the images came back. Titan's atmosphere, rich in methane and nitrogen, was far too dense for Voyager's cameras to penetrate. After its flyby of Titan, Voyager 1 ascended above the plane of the solar system. From there, it was on a course that would take it beyond the outer planets and into interstellar space. Before it continued its journey, Voyager 1 captured one final image of Saturn, taken from an angle no probe had ever achieved. This image, with the majestic planet framed against the darkness of space, marked the end of Voyager 1's planetary encounters. Nearly 10 months later, its sibling spacecraft, Voyager 2, would reach Saturn, but from a slightly different path that would allow it to continue on to Uranus and Neptune. Unlike Voyager 1, Voyager 2's high-definition camera was still functioning perfectly, and scientists were eager to receive high-quality images. The pictures did not disappoint. They revealed that Saturn's rings were far more intricate and dynamic than previously understood. Variations in density and structure created complex patterns that stunned researchers. Interestingly, when comparing Voyager 2's observations with those from Voyager 1, scientists noticed changes in the ring's appearance, suggesting that Saturn's rings might be more dynamic and variable than once believed. The rings themselves, named with letters in the order of their discovery, stretched between 7,000 and 880,000 kilometers above Saturn's equator, yet their average thickness was a mere 30 meters, razor-thin on a planetary scale. One of the standout discoveries from Voyager 2 was its imaging of Enceladus, one of Saturn's smaller moons. The surface of Enceladus appeared icy, cracked, and strangely uncratered in some areas. Beneath this icy shell, scientists theorized, might be a liquid ocean. Voyager 2's flyby didn't confirm this theory but provided enough clues to keep Enceladus on the radar for future missions. Eventually, after its work at Saturn was complete, Voyager 2 left the system. It did not enter orbit around the planet as it needed to preserve momentum for the rest of its mission, toward Uranus and Neptune. It would be more than 2 decades before another spacecraft returned to Saturn. That return came with the launch of the Cassini spacecraft in 1997. Cassini was a joint mission between NASA, the European Space Agency (ESA), and the Italian Space Agency. This was no ordinary spacecraft, it was the most sophisticated and massive interplanetary probe ever built at the time. Cassini carried 12 advanced instruments, each one overseen by a specialized team back on Earth. These teams worked around the clock, preparing to interpret the vast flow of data Cassini would send home. It took Cassini over 6 years to reach Saturn, finally arriving in July of 2004 to begin its long-anticipated mission. To communicate with Earth, Cassini used a high-gain antenna for high-speed data transmission. Interestingly, this antenna was also repurposed for protective maneuvers. During what's known as a ram maneuver, it served as a makeshift shield, protecting the spacecraft from micrometeoroid impacts, especially during crossings of Saturn's ring plane. On July 1, 2004, Cassini executed its orbital insertion by firing its engine for a carefully calculated 106-minute burn. Because the spacecraft was temporarily hidden behind Saturn during this burn, mission controllers at JPL couldn't monitor it in real time. Telemetry was recorded for later playback, making the wait both tense and exciting. Cassini was built not to fail. In addition to its primary engine, it had a backup, along with 16 monopropellant thrusters, 8 for primary use and 8 for redundancy. Unlike the Voyager probes, which recorded data on mechanical tape, Cassini used a modern solid-state recorder. Its first orbit around Saturn followed a wide, elliptical path that carried it past Titan, an intentional design. Titan's gravitational pull was crucial for adjusting Cassini's course and expanding its observational reach to Saturn's other moons. But more importantly, Titan itself was a major scientific target. Its dense, hazy atmosphere made it a mystery worth solving. To explore Titan more closely, the European Space Agency had designed a small lander called Huygens, which was attached to Cassini. On Cassini's second approach to Titan, the Huygens probe was released. Equipped with a heat shield, parachute, and battery power to last several weeks, Huygens began its descent. Over the next 20 days, the probe drifted over 4 million kilometers toward Titan. 3 days after detachment, Cassini adjusted its trajectory to avoid collision and positioned itself to receive data from Huygens as it descended into Titan's thick atmosphere, marking the first-ever attempt to land on a world in the outer solar system. As Huygens entered Titan's atmosphere, it began sampling gases and capturing images during its descent. The landscape beneath the clouds came into view, revealing gentle hills, smooth plains, and channels etched by flowing liquid. Interestingly, the surface showed few impact craters, and those present appeared heavily eroded. These observations painted a picture of a geologically active world. When Huygens touched down, it became the first human-made object to land on a celestial body beyond the asteroid belt. The images it sent from Titan's surface showed rounded rocks, believed to be composed of solid water ice, smoothed by erosion likely caused by liquid methane and ethane. Titan proved to be unlike anything seen before. It had weather systems, erosion, and features similar to those on Earth, but the chemistry was entirely different. Instead of water, the rain on Titan was made of liquid hydrocarbons. Rivers and lakes weren't formed by H2O, but by methane and ethane. Cassini continued orbiting Saturn, using radar to map Titan's hidden surface, confirming the widespread presence of hydrocarbon lakes. The discovery of rainfall, weather patterns, and surface erosion on Titan made it a prime candidate for studying prebiotic chemistry, and perhaps even the potential for primitive life. While Titan captivated scientists, another small moon began to steal the spotlight, Enceladus. At first glance, it appeared like a bright, frozen marble, one of the most reflective bodies in the solar system. Its surface was a mix of cratered terrain in the north and strange linear fractures in the south, known as tiger stripes. On Cassini's first flyby of Enceladus, the spacecraft's magnetometer detected something unexpected, a subtle deflection in Saturn's magnetic field, as if Enceladus had a thin atmosphere. On the next pass, the same anomaly appeared again, prompting scientists to request a much closer flyby. Cassini's flight path was adjusted so it would pass just 175 kilometers above Enceladus. What it found was astonishing. Plumes of water vapor were erupting from the moon's south pole, spewing out through the tiger stripe fractures. The plume contained not only water vapor but also salt and trace chemicals. Over the years, Cassini would perform 24 flybys of Enceladus, with the closest skimming just 25 kilometers above the moon's icy surface. With each pass, Cassini's instruments gathered more data, uncovering a moon that was far more dynamic and intriguing than anyone had expected. Unlike Mars, where rovers searched tirelessly for evidence of ancient water, Enceladus seemed to be shouting its secrets into space. Gravity measurements revealed the presence of a global ocean beneath the ice shell. Infrared instruments detected heat coming from the fractures. More surprisingly, those plumes contained silica particles, hydrogen, and a variety of organic compounds. The presence of hydrogen strongly suggested hydrothermal activity, hot water interacting with rock at the seafloor. This hinted at the existence of hydrothermal vents, like those found deep beneath Earth's oceans, where life can thrive in complete darkness. At only 500 kilometers in diameter, Enceladus was far too small to sustain internal heat through radioactive decay alone. Tidal flexing, gravitational squeezing by Saturn, explained some of the heating but not all. The temperature readings from the moon's south pole were unexpectedly high. Scientists were left puzzled yet thrilled. Enceladus checked nearly all the boxes for potential habitability. It had liquid water, organic molecules, a heat source, and dynamic geological processes. The only unknown was whether these conditions had remained stable long enough for life to emerge. Back on Earth, researchers drew comparisons between Enceladus and Earth's deep ocean hydrothermal vents. These are environments where life not only exists but may have even originated. Could Enceladus host similar ecosystems in its hidden ocean? Many scientists now believe that this icy moon could be the best place in the solar system to search for extraterrestrial life. It wasn't just speculation anymore. This was science backed by direct evidence. It took time, but eventually, Cassini reached the ideal position to capture backlit images of Enceladus's plumes, providing a dramatic view of their reach and volume against the sunlight. One of the most iconic images captured by Cassini showed Saturn with the sun directly behind it. This rare alignment revealed the elusive E-ring, Saturn's outermost, faint ring barely visible in normal lighting. What made this image extraordinary was the realization that the E-ring was being continuously replenished by the geysers of Enceladus. The tiny moon, once an afterthought, had become one of the most scientifically important objects in the solar system, reshaping our understanding of where life might exist beyond Earth. Saying that Saturn has 62 moons is actually a bit misleading. If you look closely, each individual particle within Saturn's magnificent ring system could technically be seen as a moon in its own right. These countless fragments orbiting the planet form a massive family. There are the large inner moons, the large outer moons, shepherd moons that shape and guide the rings, co-orbital moons that trade places in a celestial dance, and even moons that orbit other moons. Each one is unique. During the Voyager missions, interest in these moons wasn't the priority. But for the Cassini mission, close and intentional examination of Saturn's moons was baked into the plan from day one. One of the more mysterious moons Cassini examined was Iapetus, which orbits Saturn beyond Titan. It was first discovered in 1671 by Giovanni Cassini himself. At the time, he noticed it as a tiny dot of light to the west of Saturn, but oddly enough, he couldn't see it when it was supposed to be on the east. The reason? Iapetus has a bizarre dual-colored surface. One side is bright and the other is pitch black. And since the moon is tidally locked to Saturn, meaning one face always points forward in orbit, the dark side always leads. A leading theory is that it sweeps up dark debris coming from Phoebe, a more distant and darkly colored moon. But that's not all. Iapetus also features one of the strangest geological features in the solar system. A massive ridge that runs along its equator, stretching more than halfway around the moon. This ridge is twice the height of Mount Everest, which is extraordinary considering Iapetus is only about 1,500 kilometers across. This towering ridge gives the moon a distinctive walnut-like appearance. How this ridge formed remains one of Saturn's enduring mysteries. Some scientists think it could be the remnants of an ancient ring system that collapsed onto the surface. Others believe it's related to the moon's rotational history or internal geologic processes. Cassini's precise maneuvering made all of this exploration possible. Carefully timed bursts from the spacecraft's main engine allowed engineers to tweak its orbit around Saturn, enabling flybys of different moons, detailed surveys of ring structures, and focused looks at Saturn's atmosphere. The gravitational pull from Saturn's moons, especially Titan, was cleverly used to adjust Cassini's path while conserving fuel. Cassini performed so effectively that NASA approved not just one but 2 mission extensions. Still, its fuel wouldn't last forever. NASA engineers planned the riskiest and most exciting phase of the mission for Cassini's final year, a series of death-defying orbits closer to Saturn than any spacecraft had ever gone before. Beginning in late 2016, Cassini entered what scientists called the ring-grazing orbits. These were designed to take the probe just beyond the outer edges of Saturn's rings. Each of these daring loops allowed Cassini to collect data from the very heart of Saturn's ring system. Instruments like the Cosmic Dust Analyzer and the onboard mass spectrometer began to sample particles and gases as the spacecraft darted in and out of the ring plane. During its 251st orbit, Cassini passed over Saturn's north pole, capturing stunning new details of the giant hexagonal storm system, a strange weather formation first glimpsed by the Voyager spacecraft decades earlier. That hexagonal storm, over twice the width of Earth, has maintained its geometric shape for decades. As Saturn moved into its summer season, Cassini noticed the storm changing color, revealing complex atmospheric behaviors. At the center of this hexagon is a fierce cyclone, captured in false color imagery, red indicating lower clouds and green marking higher ones. Winds at the storm's perimeter howl at over 540 kilometers per hour. It's like nothing else in the solar system. But observing this weather system was not without challenge. One of Cassini's magnetometers had failed early in the mission, forcing engineers to occasionally roll the entire spacecraft just to recalibrate the instrument manually. Cassini completed 20 of these ring-grazing orbits, each one mapped out with scientific precision. Nothing was left to chance. As the Sun aligned almost directly behind Saturn's rings, Cassini took advantage of the backlighting to look for faint dust clouds and ultrafine particles. Something was clearly grinding the rings down into powder. To investigate, Cassini performed radio occultation experiments, beaming radio waves of multiple frequencies through the rings toward Earth. By comparing how the signals were altered, scientists could deduce the size and composition of the particles. One striking image of the A ring, the outermost bright ring, used false colors to show where particles were larger than 5 centimeters red, smaller than 5 centimeters green, and smaller than 1 centimeter blue. These images and data revealed something profound. Saturn's rings are more dynamic and short-lived than previously believed. The gravitational pull from Saturn and its many moons creates gaps in the rings at very specific, mathematically predictable locations. Before Cassini's arrival, scientists had only catalogued 18 Saturnian moons. That number later exploded to 62 confirmed moons. Among them are Prometheus and Pandora, shepherd moons that maintain the structure of the thin F ring. Prometheus orbits on the inside edge, while Pandora runs along the outer boundary. Their gravitational influence keeps the ring tightly confined, like cosmic gatekeepers holding back chaos. Then in April 2017, Cassini's orbit was altered again, marking the beginning of its final chapter. Now the spacecraft would dive between the innermost ring and Saturn's cloud tops, an incredibly narrow and dangerous space. This maneuver was unprecedented. And although it would ultimately end with Cassini's destruction, the data gathered from these inner plunges would complete humanity's most detailed picture of a gas giant ever attempted. NASA decided it was better to send Cassini to a fiery end than risk it drifting uncontrollably and potentially contaminating one of Saturn's moons, some of which may harbor the ingredients for life. As Cassini got closer to the planet, its instruments picked up an eerie phenomenon, a constant stream of particles raining down from the rings onto Saturn. This ring rain includes fine dust and ice, pulled down by gravity toward the planet's equator. At higher latitudes, charged particles spiral along magnetic field lines. This means Saturn's rings are actively feeding material into its atmosphere, a process far more intense than previously imagined. Scientists now estimate that around 10,000 kilograms of ring material falls into Saturn every second. At this rate, the rings may disappear entirely within the next 100 million years. Adding to the mystery, Cassini detected something even stranger, an electric current flowing between the inner D-ring and Saturn's upper atmosphere. This electrical interaction suggests a more complex relationship between the rings and the planet than previously thought. Toward the end of its final orbits, Cassini began dipping into the very top of Saturn's atmosphere. At this stage, all stored data had already been transmitted. Now real-time communication was all that remained. Thrusters had to work continuously to keep the spacecraft steady and its antenna pointed toward Earth. Cassini's final tasks included sampling atmospheric particles and precisely measuring Saturn's magnetic field. Then came the moment engineers had both anticipated and dreaded. The final transmission came through, a last data packet sent across the 1.4 billion kilometers separating Saturn from Earth. 84 minutes later, the signal ceased. In those final moments, engineers and mission control could do nothing more than watch and listen. Within the next 45 seconds the spacecraft was gone. It had plunged into Saturn's atmosphere, where it was torn apart and vaporized. But Cassini's legacy lives on. The mission reshaped our understanding of Saturn, its rings and its many moons. It will take years to fully analyze the treasure trove of data the spacecraft left behind. As of now, there are no new missions to Saturn officially scheduled, leaving Cassini's final descent as the closing chapter of human exploration at the ring giant, at least for now. Observations of Jupiter's Great Red Spot continue to fascinate astronomers. This massive storm, larger than Earth itself, has been raging for centuries. Some scientists believe it's the same feature that early observers noticed hundreds of years ago, while others suggest it's a recurring atmospheric phenomenon. When Voyager 1 made its closest approach to Jupiter in March 1979, anticipation at NASA's Jet Propulsion Laboratory soared. The flybys were designed for maximum data collection during brief, intense periods. After long stretches of silence in deep space, the sudden flood of data as the spacecraft passed close to planets was both thrilling and overwhelming. One of Voyager's most revolutionary contributions was how it changed our view of Jupiter's largest moons, the Galilean moons. Once seen as mere points of light, Voyager's close-ups revealed that these worlds were completely unique and far more complex than expected. The first surprise was Io, the innermost large moon. Instead of being cold and barren, it appeared yellowish with odd, active plumes. A long-exposure image captured what turned out to be a massive volcanic eruption. Thanks to tidal heating from Jupiter's gravity, Io's core remains hot, and these eruptions blast material hundreds of kilometers into space. Voyager 2 followed 3 months later in July 1979, passing closer to different moons. It gave us our first good look at Europa, which stunned researchers with its smooth, bright surface, the most reflective in the solar system. Patterns on its surface resembled cracked polar ice on Earth. Scientists concluded that beneath Europa's frozen crust lies a global ocean. Like Io, Europa is internally heated by Jupiter's immense gravitational pull, which keeps this subsurface ocean in a liquid state. Voyager 2's flyby added to a treasure trove of questions and mysteries left for future missions to unravel. While Voyager moved on to Saturn, the data it left behind kept researchers busy for years. Though Voyager transformed our understanding of the Jovian system, it also left huge gaps. It would be over a decade before another mission reached Jupiter. In October 1990, NASA launched the European-built Ulysses spacecraft aboard the Space Shuttle Discovery. Although Ulysses was meant to study the Sun's poles, it needed a gravity assist from Jupiter. This slingshot maneuver bent its flight path out of the solar system's plane, called the ecliptic, allowing it to enter a rare polar orbit around the Sun. Ulysses wasn't alone in using Jupiter's gravity. NASA's Cassini probe to Saturn, launched in 1997, and the New Horizons probe to Pluto in 2006 also used Jupiter flybys to shorten their journeys dramatically. These brief encounters weren't just navigational tricks. They provided chances to gather more data about the gas giant. Meanwhile, in NASA's Jet Propulsion Laboratory, a new spacecraft was under construction, Galileo. It would be the first probe to enter orbit around Jupiter. Its large 4.8-meter antenna was designed to unfold like an umbrella during flight, but its mission faced several delays. Originally set to launch in 1986, Galileo was grounded after the Challenger disaster. Eventually, it launched aboard Shuttle Atlantis in October 1989. However, safety regulations meant a less powerful upper stage booster had to be used, so Galileo took a new path that first sent it toward Venus for a gravity assist. Because of the new route, which brought it closer to the Sun, engineers decided to delay deploying the sensitive antenna until after its second flyby of Earth. Unfortunately, by that time the antenna only partially opened. Lubricant had dried during storage and all recovery efforts failed. With its main antenna compromised, Galileo had to rely on its smaller backup antenna, resulting in a much slower data rate. Still, the spacecraft continued its journey. Along the way, it flew past asteroids including Ida, the first asteroid ever discovered to have a moon, Dactyl. In July 1995, 6 months before reaching Jupiter, Galileo released a small atmospheric probe. This probe descended into Jupiter's atmosphere, sampling gases and recording data for just over an hour. To scientists' surprise, it detected very little water vapor and unusually low levels of helium, challenging long-held assumptions about Jupiter's composition. The probe also measured extreme temperatures, revealing significant heat from Jupiter's interior. Shortly after the probe completed its mission, Galileo fired its main engine for nearly 50 minutes to enter orbit. Due to Jupiter's intense radiation belts, engineers planned a second engine burn to adjust the spacecraft's orbit, keeping it above the most dangerous zones. Galileo's first orbits brought it close to Ganymede, Jupiter's largest moon. But technical troubles soon emerged. The spacecraft's tape recorder, now crucial due to the failed antenna, became stuck in rewind mode for 15 hours, suffering radiation damage that degraded its performance. Galileo's team realized radiation was taking a toll on all systems. Light-emitting diodes used to control the tape recorder began to fail. Despite these setbacks, the second orbit again brought Galileo near Ganymede. During these close passes, it discovered that Ganymede is the only moon in the solar system with a magnetic field. Evidence also emerged of an ocean trapped between layers of ice. Galileo's trajectory was slightly adjusted for each orbit to allow close encounters with different moons, but these passes often took the spacecraft dangerously close to radiation-hot spots around Jupiter. Europa was of special interest to scientists. Multiple instruments confirmed that a salty ocean exists beneath its icy shell. Years later, reanalysis of Galileo's data revealed something even more exciting. Faint magnetic signatures and plasma waves showed that water plumes were erupting from Europa's surface. This suggested the ocean might not be sealed off completely, it could interact with space, potentially allowing life-sustaining chemistry. Meanwhile, Io's tidal heating was more dramatic than anyone imagined. Galileo observed that its surface was flexing by over 100 meters and that its volcanoes were hotter than anything found on Earth. Galileo orbited Jupiter for 8 years, completing 35 orbits and drastically expanding our knowledge of the Jovian system. However, the mission was plagued by hardware degradation from constant radiation exposure. The spacecraft's systems suffered frequent resets and malfunctions. Engineers worked tirelessly to implement software changes that allowed Galileo to recover automatically after these faults, minimizing data loss. Despite these difficulties, Galileo achieved more than anyone had hoped. The experience led to critical design changes for future missions to Jupiter. Engineers knew any new spacecraft would need better radiation shielding and more robust systems. In August 2011, a new mission named Juno began its journey to Jupiter. It would take nearly 5 years to arrive. Unlike Galileo, Juno had a very different focus. Instead of studying the moons, it would concentrate entirely on Jupiter itself. All its critical electronics were housed inside a heavily shielded titanium vault to protect them from radiation. Instead of using a plutonium-based power source like previous missions, Juno relied on solar panels, the largest ever sent beyond Mars. A shortage of plutonium-238 had forced this design shift, but it worked remarkably well, even in the dim sunlight around Jupiter. Juno followed a unique path, looping out past Mars before swinging back to Earth for a gravity assist. This added a massive 14,000 kilometers per hour to its velocity, propelling it on a trajectory toward Jupiter. It approached the giant planet from above its north pole, entering a polar orbit. This orientation helped Juno avoid Jupiter's deadly radiation belts, which encircle the equator. Just days before closest approach in July 2016, Juno switched to autopilot mode. On July 4, it began its engine burn to slow down and enter orbit. Tension ran high until confirmation finally reached Earth. The mission team cheered in relief as Juno executed the insertion perfectly. Equipped with instruments capable of peering deep into Jupiter's cloud layers, Juno began mapping the planet's atmosphere in 3 dimensions. The polar orbit allowed it to study Jupiter's poles for the first time. The images it returned stunned scientists. Jupiter looked completely different from the striped appearance we'd known. Juno was scheduled to switch to 14-day orbits after 2 long initial loops, but an issue with its helium valves made engineers keep the original 53-day orbit. Fortunately, an extension was granted to continue the mission. Soon after the valve issue, Juno entered safe mode. All instruments shut down and some data was lost. The glitch resembled past problems from the Galileo era, but this time the team traced the problem to a faulty data transfer from one instrument. Once isolated, the spacecraft resumed normal operations. Juno's polar view also revealed bizarre storm patterns. At the North Pole, a central vortex is surrounded by 8 cyclones arranged in a geometric pattern. At the South Pole, 5 similar storms ring another central cyclone. These storms all rotate in the same direction, yet never merge or dissipate. On its 7th pass, Juno flew directly over the Great Red Spot. Its microwave radiometer mapped heat patterns deep within the storm, down to a depth of 350 kilometers. It found significantly higher temperatures at deeper levels, indicating powerful convection currents. Unlike Earth, Jupiter has no solid surface for storms to weaken against, so this massive vortex remains intact. The Great Red Spot sits 22 degrees below the equator and has drifted around the planet several times since observations began. Thanks to Juno, we're finally starting to understand the physics behind Jupiter's most iconic feature. Jupiter's magnetosphere is the largest structure in the solar system, extending far beyond the planet itself. It's powered by Jupiter's rapid rotation and internal dynamo. Juno has helped scientists visualize how this immense magnetic field interacts with charged particles, generating powerful auroras at the poles. These auroras are many times stronger than anything seen on Earth. As Juno continues its mission, it's answering questions raised decades ago by Voyager and Galileo while opening new mysteries. Each pass brings more clarity and more wonder. Jupiter, once just a bright light in the sky, now reveals itself as a dynamic, ever-changing giant.